Alrighty, P 19.6, free energy and temperature, which means now we're going to start to change that temperature. If there is ever a chart that is beyond important, it's this one. Okay, and I even put it down below. This is the one that AP curriculum gives us, but I've always used this one down here at the bottom, but it's the same thing. Okay, so when I say need to know, it's like to save your life when it comes to this topic of tying in delta H and S and G together. What if they don't want you to calculate? What if they want you to make predictions of the signs? So this whole thing, ladies and gentlemen, as you're going to see right here, what if there is no calculation? So explain whether a physical or chemical process in which thermodynamically favored based on that delta G. Okay, so in general, temperature conditions for any process to be thermodynamically favored, we want that negative delta G, can be predicted with signs of H and S. Okay, so can you predict with no math what the sign of delta H would be? Okay, so I'm going to go over this chart a little bit down here instead. But this was a little bit of Doc Dina. When she does her video, you'll see her doing this also. In cases where the delta H is negative and the S is positive, okay, so they're obviously in opposite signs. So negative versus positive. No calculation of delta G is necessary to determine that the process is thermodynamically favored, because when H and G are the same sign, because right here it would also be negative, when H and G are the same sign, they will be thermodynamically favored. And as you see right here, H is negative, calculating for G is negative. It will always be thermodynamically favored at every temperature, high temperature, low temperature, any temperature. It will be thermodynamically favored. In cases where delta H is now positive and S is negative, no calculation of delta G is necessary to determine that thermodynamically is unfavored, because your delta G will be positive. See how the H and the G go hand in hand? When it does that, see how it goes H and G right there is positive? Not thermodynamically favored at all temperatures. Okay, so one is thermodynamically favored and the other one is not. When these two are the same signs, okay, they will either be thermodynamically favored or not. Okay, so this is predicting without doing any math. Okay, explain the relationship between the solubility of a salt and changes in entropy and entropy that occur in the dissolution process. Now, I threw this video in. It was at the very end of Unit 7. You didn't do it then because it has to do with this topic. So what happens to entropy and entropy and Gibbs free energy when it has to do with the dissolution process? Okay, so you're going to see this video. It's at the very end of your AP. I was putting it on there. See right there? I put it right there, 9.6. And then you're going to watch the Gibbs free energy for the dissolution. One video, okay? Gibbs free energy, delta G, for dissolution of a substance reflects a number of factors, okay? So it's all about the dissolution of that. So number one, the breaking of those intermolecular forces that hold that solid together. I mean, are you talking about some London dispersion, dipole-dipole? What are we talking about? The reorganization of the solvent, aka water, of the dissolved substance, and the interaction between the dissolved substance and the solvent. You heard in one of my videos, okay, and I think it was in 19.4, about how the solid, when it turned into an aqueous form, you created disorder. Okay, your entropy increased, but the solvent, aka the water, actually became more ordered. So your entropy kind of goes down. Either way, the dissolution trumps it. Okay, so even though you got one creating disorder, the other one's actually creating more order, the dissolution still trumps the whole situation. So it's possible to estimate the sign, okay, and the magnitude, how big of it is, for delta H, delta S, contribution to these factors of what's going to happen to delta G. Making predictions for the total change in Gibbs free energy for dissolution can be challenging due to the cancellation among these free energies associated to those three factors. So you have to make predictions, ladies and gentlemen, and it's going to be tough because one, you have to pay attention to temperature, but now we're throwing chapter 11 back into the mix here, chapter 11, how those forces can also change Gibbs free energy too. So let's look at this chart. Delta G, we already know, tells us thermodynamically favored. Okay, so when H and G, pay attention to H and G, are they the same sign? And that correlates to all temperatures. It will always be whatever it is, thermodynamically favored or not, when it's at the same signs. It's when H and G may not be the same sign. Okay, so let's look at these two down here. When H and S are the same sign. Because notice in the first two boxes, they're opposite signs. Okay, so when these two are the same sign, it helps, ladies and gentlemen, because you're going to see me do this, plug in some positives and negatives into this. So let's say right here, we'll call this scenario number 1. If H is negative, and you know T is positive because we're talking about Kelvin here. Kelvin's always positive. And what if the S is negative? That means you're taking a negative minus a negative number, okay? And what's going to happen to that when you have that negative minus a negative number? Well, it's going to become a little positive, okay? So now this part right here, the negative minus the negative, it will be thermodynamically favored if it's at low temperatures, okay? So if we want thermodynamically favored, depending on what this H is, because that's the hard part. We don't know if it's a high value or a low value. So I'm right here, if this was a low temperature number, minus, let me put this over here, whatever that H number was, that's minus, and then minus a low negative number, which means now it's going to become positive. This negative should be still a higher value, which means the answer will still be negative as long as it's at a low temperature, okay? Because what if that temperature number was a very high number? So now right here, same scenario, what if this was still, let's do like in a different color. Let's go right there. So this right here, that was the pink right there. So let's go maybe a little green, okay? So what if H is still negative minus a big temperature? And when we say like big and small, ladies and gentlemen, it's always about referring to that 298. Is it greater than that 298 or is it a little bit less than that 298? So we're talking about a big, big positive number, okay? So negative minus a big number times that negative number right there. So big positive times this negative right here. This potentially could outweigh it, okay? So right here, you could get a delta G that's positive, which means it is not thermodynamically favored at those very high temperatures. And I know you're like going, OMG, Rodriguez, I have no clue like what you're doing. It's predictions, okay? It's you have to pay attention to what that temperature is doing, okay? Let me do another one. Let's go a little blue here, okay? So we'll go right here, blue. Okay, what if H and S are the same? So delta G, delta H, T, delta S, okay? And for the first scenario, okay, we want that negative. So that means this is a positive number minus, we already know temperature is positive, and let's say if H and S were both positive. I have a positive minus a positive number, okay? Well, right here, it would be thermodynamically favored if that was a high positive number. Because remember, you're taking a positive minus a positive. So positive minus positive right there. What happens to this value right here if it's like a big positive or a low positive? Okay, so right here, If they're both positive, the only way it'll be thermodynamically favored is if it's at a very high temperature. Because what's going to happen is if this number is bigger and bigger, a small number minus a big number, well, that means that delta G is going to be negative. But that's only at high temperature. Okay? And if I take it on the flip side, let's go a little bit orange, when would it not be thermodynamically favored? So if I take now my H right here, still positive, minus H is still, T is still positive, and S is still positive. But what if this right here was a very low temperature? If it's a very low temperature, I still get a positive minus a positive number. But remember, this number right here is very small. That means that this delta H is going to be trumping this calculation, which means I'm going to get a positive. Maybe it's making a little sense to you, maybe not until we do an example, which you know I'll give you an example. And then right here, this would be at very low. So when you tackle this chart, ladies and gentlemen, let me tell you how I do it, okay? I concentrate on one of the lines. I concentrate on this one. Because I know if H and G are the same sign, it's thermodynamically favored, okay? And then I tackle this line. And why do I do the first and the third? Because this first line, look at this first line. If they're both the same sign, I know that it's going to be thermodynamically favored at every temperature. Because if it's opposites, then it's not going to be thermodynamically favored at every temperature. So why memorize 4 lines when you can cut it down into 2? Know the opposite. So then I tackle this third one. Well, what if H and S are both negative, and then comes down to these two? If I want it to be thermodynamically favored, I know that it's thermodynamically favored at low temperatures, okay? Same thing right here, positive and positive. And if I want it to be, I always just remember when it's thermodynamically favored. When a positive positive, it will only be thermodynamically favored at high. Don't try to tackle the whole chart. Find ways to know part of it, because then the opposite is just the opposite, okay? So let me show you how to use this as in a prediction. So I just grabbed this example real quick. The Haber process, back in chapter 14, was all about the production of ammonia, how it took that nitrogen gas and reacted with that hydrogen, a very, very famous reaction on how to produce fertilizer. And you get that 2 ammonia, okay? And this was at an equilibrium state. Assuming that H is negative and S is negative for this reaction, and let's just say that temperature has no effect on it, okay? Predict the direction in which the reaction changes with increasing temperature. So what happens if temperature changes? What would happen to the direction? Will it still be spontaneous in one direction, or would it actually be spontaneous in another direction? Okay? So that temperature right here, making some notes here, temperature is very dependent on that delta G. Okay? And so that delta G, you have to use this equation and look at what's going to happen. Okay, so I know my delta H is negative, and I minus, we know temperature is positive, and it says right here, what's going to happen to delta G if this number gets bigger and bigger and bigger? And my delta S is negative 2. Okay, so I got all these variables. Now what I do notice is that these two are the same sign. And remember what happens when they're both the same sign. Okay, well that means it's not always going to be, thermodynamically favored at all temperatures. Because remember, the H and the S have to be opposite signs for it to be thermodynamically favored. In this case, they're both the same sign. So I'm kind of looking at this scenario right here, the third box. When S and H are the same sign, in this case they're both negative, I have to figure out which one is going to be thermodynamically favored. Okay, so if it's increasing temperature, let me kind of clean this up right here. It looks like a little equal sign there. So I'm going to put right here minus, we'll make that in green, minus. So a negative number minus a higher positive temperature with a negative number. Okay, so what's going to happen? We can expect that S to be negative because we know it's a negative. And how do we know it's also negative? Because look at what's happening here. I have 4 moles of gases and I produce 2 moles of gases. I have actually decreased my entropy because I created more order. Okay, which you saw us do this in the video of not in the video, but as in the homework for 19.4, okay, which was on Monday. So I've actually created more order because I have less gas that was produced in this reaction, okay? So because this T delta S, I have a negative times this positive and negative part right here, what's going to happen to this, let me do it in color. So I still have my H is negative, and this minus this negative number, well, this is going to turn out to be positive right here because minus this negative, it's going to become positive with increasing temperature. And as we keep increasing and increasing, this number is just going to get bigger and bigger and bigger. Okay, so as a result, what's going to happen to delta G? Well, delta G, what's going to happen to it? Okay, it's going to either, you could say it a couple different ways. You could say delta G is going to become either less negative, or you can say more positive. Okay, he's either going to be less negative or more positive with increasing temperature. Okay, because in the end, ladies and gentlemen, what if this value right here for temperature keeps going higher and higher and higher? Well, that means in the end, my delta G has the potential to get positive. And so if you look at the chart right here, third line right here, okay, it will be, if it's positive, right there, positive, that means it will not be thermodynamically favored at high temperature. And look, we already did it. But we have to show AP how we're going to predict it. And how you predict it is literally using all these minuses and pluses, okay? But you have to tell them what you're doing at the same time. So the delta G will actually become either less negative. It potentially could still be thermodynamically favored, but we're assuming this delta T is just getting bigger and bigger and bigger. Like we were saying, what if it gets like 500? That's huge compared to like 25 degrees Celsius. So it will probably be, okay, so I'm making my prediction of delta G. The delta G will become not thermodynamically favored. I'm only abbreviating that, ladies and gentlemen, because of time, okay? Not thermodynamically favored with increasing temperature, okay? So as you keep increasing temperature and temperature, it's just going to become more and more not thermodynamically favored. So the driving force for this production of ammonia becomes even smaller with increasing temperature. And so we're going to mention that, and producing NH3 will be less, or actually you could say will be smaller with that increasing temperature. You're just going to produce less and less and less of it. And producing NH3 will be less, I guess, and less over time. Okay, as long as that temperature keeps increasing, it's just going to get smaller and smaller and smaller. Okay, all right, so now let's actually plug it in so we can show them how it actually is going to be positive. So first at room temperature versus high temperature. Okay, now we just said right here, assuming that delta H and S aren't going to change with temperature. So when I plug it into my equation right here for delta G and delta H, T delta S, I can still use these H's and the S since no effect with increasing temperature. They said it right there, so I can keep using it. Because if it actually did make a difference, we would have to use products minus reactants 2 times, okay? Because that temperature would be different. But they said it doesn't make a difference. So we're going to solve for delta G. And right here, we're going to say first the one at room temperature. So delta G, we have our H is negative 92.38 kJ per mole minus the temperature. Now remember this temperature, we got to get it into Kelvin. So 298 Kelvin. Okay, so making some notes here. Temperature better be in Kelvin. And here's the next big one, your delta S. Convert units. Okay, right there I have J over K times mole. I need this guy to be in kilojoules. So we're going to move that decimal. So negative 0.1983 kJ mole times K. All right, so we're going to plug that in. I don't know why you always put my calculator away. All right, so let's tackle this part right here. So 298 times that negative number, 0.1983. So this portion right here is negative 59. I'll use 3 sig figs, 59.0. And now I just have kJ, oops, kJ. I don't know what's going on over there. Kelvin's gone, so kJ per mole. But I have a negative minus this negative number. Okay, so obviously this part's going to turn out positive, but this negative is still dominating it. So in the end, let's plug it in, 92.38 and that 59.0. So that negative 92 and this negative and negative, it's going to cancel, become positive. So I'm going to be stuck with, looks like 1 sig fig after. So 33.3 kilojoules per mole. Okay. So right here, 298, that's actually considered like a low temperature compared to that 500. So at low temperatures, I was thermodynamically favored. Okay, and if you go right here to the chart, H and S both negative right there, negative and negative. I know there's so many circles on here, negative and negative. The only way I would be thermodynamically favored is at low temperature. Okay, now let's try it at a high temperature. So right here, now at 500 degrees Celsius, which this is going to turn out to be 500 plus 273 is 773. All right, use the same equation, just throw in a different temperature. Because they said that delta H did not matter and delta S did not matter if that temperature changes. So 9238. And I know, ladies and gentlemen, when you are asked to predict, that scares you sometimes because you are so much better at it when it comes to math. And don't get scared of that. Go with the gut. But I understand because I'm the same way. I like to do it with math. I like to explain it with math because it makes sense to me mathematically. But that's what makes you different between AP versus honors versus CP. You have to be able to explain it in words, okay, without using the math. And that's what makes AP AP. So can you explain this as in part A just by looking at positives and negatives? And once you see the difference in the math, I think it's going to make more sense to you what we just did right there in part A. Okay, so now right here we have this higher temperature. Okay, so we still have this negative right here, and we're going to multiply the temperature times delta S. So 773 times that 0.1983, and then this part right here, I'm still going to get a negative 153, and we'll just call it 3 sig figs. So Kelvin is gone. So kJ per mole right there. Okay. And now look what happened. This is now going to trump it because negative minus this negative number, this right here, is going to become positive. Just like up there. It's going to become positive right there. But now this right here in this temperature is now controlling it. The entropy and the temperature, because it's higher, is now controlling it. So that means that in the end, this will be positive. And what did we say right here? With increasing temperature, it will be positive. It's not going to be thermodynamically at this higher temperatures. So let's plug this in. So negative 92.38. And now this positive 153 with nothing after the decimal, 60, it says 60.6, so we're going to go 61 kJ per mole. And there it is, ladies and gentlemen, right there. Now it is not thermodynamically favored at high temperature. You made that prediction up there. I just want you to see how AP does it both ways. It's actually a learning objective. So they literally put it in the chart because they want you to make predictions. And I believe Doc Dina, as you see her name right there, that's her last name, she's going to show you how to use this chart too in one of the videos, okay? All right, AP, we're almost done with thermal. We got one last one.